Welcome to Shanti-Peace for Mathematics. In this video, we are discussing about the Fourier series in general, any interval. Till now, what we are discussing is the Fourier series you can define over the interval minus pi to pi or in the interval 0 to 2 pi. That means you have a function which is a 2 pi periodic function, then you are able to find out the Fourier series for such functions. The Fourier series of the 2 pi periodic function is represented as f of x is equal to a0 by 2 plus summation n running from 1 to infinity an cos nx plus bn sin nx, where this a0 is 1 upon pi. If the interval is minus pi to pi, then this limit is minus pi to pi. If it is interval 0 to 2 pi, then this limit is 0 to 2 pi. f of x dx. an is 1 upon pi minus pi to pi f of x cos nx dx. And the bn will be 1 upon pi minus pi to pi f of x sin nx dx. This a0, an and bn are called the Fourier coefficient of the function f of x. Now the question is, what will be the Fourier series of a function in the interval alpha to alpha plus 2 pi, or instead of 2 pi I may write down 2l. So what will be the Fourier series of a function in the interval this, or I can say it is a 2l periodic function. So the Fourier series for 2l periodic function is represented in this manner, where we can say that f of x is equal to a0 by 2 plus summation n running from 1 to infinity an cos n pi x upon l plus bn sin n pi x upon l, where your function f is an integrable function in the interval alpha to alpha plus 2l to r. This is your function, and this Fourier coefficient will be represented as a0 equal to 1 upon l alpha to alpha plus 2l f of x dx. an will be 1 upon l alpha to alpha plus 2l f of x cos n pi x upon l dx, and bn will be 1 upon l alpha to alpha plus 2l f of x sin n pi x upon l. In particular, if you want to achieve your previous expression from this expression, you just represent alpha is equal to minus pi. So if you substitute this alpha is equal to minus pi here, then you will get your interval is from minus pi to plus pi, because and it is a 2 pi periodic function. So it is L will be pi here. So if you substitute your alpha is equal to minus pi and L is equal to pi, you will get your Fourier series in the interval minus pi to pi, which is a 2 pi periodic function. Here your function is 2l periodic function, so that's why it's represented in this manner. Now let us solve a couple of examples related to this. So the question is, find the Fourier series of the function f of x is equal to e power minus x in the interval minus 1 1 with x plus 2 is equal to f of x. So what is the given is the function is a 2 periodic function. So instead of 2l, we have here it is 2. So that will imply L will be 1. we know that the Fourier series of this function, if L is 1, then here you have L is 1, what is your alpha? Alpha is minus 1 and L will be 1. So this whole quantity will be converted into the interval minus 1 to 1, and your Fourier series of this function f, which is e power minus x, can be represented as a0 by 2 plus summation n running from 1 to infinity an cos n pi x upon L is there, but L is 1, so that's why it is upon 1 plus bn sine n pi x upon 1, where we need to calculate what is a0, what is an and bn, which are the Fourier coefficients. So let us try to calculate one by one. The first one is a0, which is 1 upon L alpha to alpha plus 2L fx dx as per the definition of this a0. L is 1, so it is 1 by 1. Alpha is 1, so that is alpha is minus 1, so that's why it is minus 1 to 1. Fx is e power minus x dx, and we know that the integration of e power minus x is e power minus x upon minus 1, and the limit is from minus 1 to 1. So if you have to substitute the value, this is minus of e power minus 1. So hence this is minus sine hyperbolic of 1, and I just multiply by 2 here, so that's why it is 2 times hyperbolic of 1 we will get. Now let us calculate what is an. As per the formula, an will be 1 upon L alpha to alpha plus 12 f of x cos n pi x upon L dx. You know that L is 1, alpha is minus 1, so that's why it is minus 1 to 1. F of x is e power minus x cos n pi x dx, and we know that this formula e power ax into cos bx dx will be e power ax upon a square plus b square. In bracket we have it is a cos bx plus b sin bx. So according to this will be e power minus x upon 1 square plus n square pi square, because b is n into pi, a is minus 1 into a, that is minus cos n pi x plus b, which is n pi sin n pi x, and the limit that we have given it is minus 1 to 1. Now when you substitute 1 here, it is e power minus 1 upon 1 plus n square pi square. Inside bracket what is left, let us see that. That is, let's substitute x is equal to 1 here, this is minus cos n pi, and if you substitute 1 here, sin n pi is there. Sin n pi will be 0 for n belongs to n, or I can say z. When you substitute minus 1 here, then it is e raised to minus plus upon 1 plus n square pi square. Inside bracket, cos is an even function, so that is again we'll have minus cos n pi, and if I substitute minus here, then again it will by this, we can say that it is 0. So the quantity left is this. Now you just see that cos n pi is common out, 1 upon n square plus pi square is also common out, and this minus become plus. So finally what we have, it is an will be cos n pi upon 1 plus n square pi square into e power minus 1 plus e power 1, which I can write down as 2 times cos n pi into cos hyperbolic 1 upon 1 plus n square pi square. So that is the value of an. where n is running from 1 to up to so on. Now let us calculate what is Bn. As per the formula, we'll have it is 1 upon L alpha to alpha plus 2L f of x dx, f of x sine n pi x upon L dx. As you know that L is 1 and alpha is minus 1, this is minus 1 to 1, fx is e power minus x sine n pi x dx. Now we know that the formula integration e power ax sine dx dx will be e power ax upon a square plus b square. In bracket we have a sine dx minus b cos dx. According to this, we can write down this is e power minus x upon 1 square plus n square pi square. Inside bracket a, which is minus 1 sine n pi x plus n pi cos n pi x, and the limit that we have to substitute, which is minus 1 to 1. Now when you substitute 1 here, just observe that what is we get is e power minus 1 upon 1 plus n square pi square is the first term. Here sin n pi is 0, so this term will become 0. Here you will have plus cos n pi, that is the first quantity is left, minus, here when you substitute minus 1 here, this is e power 1 and this will become 0, and here cos is an even function, so that's why it is minus will become plus, so we will left with e power 1 upon 1 plus n square pi square n pi cos n pi, and just common out this quantities we have n pi cos n pi 1 plus n square pi square into e power minus 1 minus power minus 1 minus e power 1. So multiply and divided by 2, then this will be minus of 2 n pi cos n pi into sine hyperbolic of 1 upon 1 plus n square pi square. So finally the Fourier series of e power minus x in the interval minus 1 to 1, which we can write as a0 by 2 first value, and the a0 is we have calculated this and 2 will get cancelled, so it is sine hyperbolic of 1, which is a minus sign, plus summation n running from 1 to infinitive a0, an is this, that is 2 cos n pi into cos hyperbolic of 1 upon 1 plus n square pi square into cos n pi x plus summation n running from 1 to infinity. Dn will be this one, so it is minus of 2n pi cos n pi sine hyperbolic of 1 upon 1 plus n square pi square sine n pi x. This is the Fourier series of the e power minus x we have. Let us do one more example here of the same kind. So the question is, find the Fourier series of f of x is equal to 2x minus x square in the interval 0 to 3, and hence deduct that 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square minus 1 upon 4 square up to so on will be pi square by 12. So the solution for this problem, here first of all you have to decide what is your L. So it is a 2L periodic function, so that's why the 2L will be 3 and your alpha is 0. So therefore L will be 3 by 2. Now the Fourier series of this function can be written as e0 by 2 plus summation n running from 1 to infinity an cos n pi x upon L, but L is 3 by 2, so that is 3. Here we'll have 2, so it is 2 n pi x upon 3 plus Vn sine 2 n pi x upon 3, where you have to calculate what is a0, what is an, and what is bn. Let us try to calculate these values. The first one is a0, that is 1 upon L alpha to alpha plus 2L f of x dx. If you substitute alpha, L is 3 by 2 and alpha is 0, we'll have it is 2 by 3, 0 to 3, fx, which is 2x minus x square dx. If you integrate this, you will have it is 2x square by 2 minus x cube by 3, interval 0 to 3. If you substitute 3 here, then this is 9 minus 27 by 3. If you substitute 0, all the quantities will become 0. So you have this, but this is 9 minus 9 again, so that's why it is 0. So a0 is 0. Let us calculate what is an. As per this, the L is 2 by 3, so this is 2 by 3, 0 to 3. In the same manner, f of x cos n pi x upon L. But what is L? It is 2 by 3, so that is L will be 3 by 2. So this will be 3 here and 2 will come here. So that's why it is 2 by 3, 0 to 3, 2x minus x square cos n pi x upon 3 dx. Now we have to apply the integration by parts. In general, it is generalized integration by parts. So to apply the generalized integration by parts, your an will be 2 by 3. The condition that I am taking this is as u and this will is v. Let us recall what is that generalized integration by parts here. That is u into v. Integration, if you want to calculate u as this, integration of v1, then first derivative of u1, second time integration of v plus second time derivative, third time integration, and this will go on. The un is the nth successive derivative, so it is nth derivative of u, and this notation is the successive integration of v with respect to x. So this is the generalized integration by parts we have. So applying that one for this functions, where this is u, this is v, we will have 2x minus x square as it is. Then it is integration of cos, which is sine 2n pi x by 3 upon 2n pi by 3. Then it is minus sign, the derivative of this quantity, which is 2 minus 2x, integration of this quantity, which is cos 2n pi x upon 3 upon 2n pi by 3 square. Then it is a plus sign, the integration of this quantity will become 2, then sine, here you will have minus, this is also minus 2n pi x by 3 upon 2n pi by 3 cube, and the next term will become 0 because the derivative of 2 will become 0, so the next term will be 0. So all the further terms were 0, so we are not writing them, and the limit you will have it is 0 to 3. Now let's substitute this 3 here. You just observe that when you substitute 3 in the first quantity, that means if you substitute 3 in this quantity, this will be sine 2n pi, because 3 will be cancelled, and which is 0. Here when you substitute 3, that is 2 minus 6, so that will be minus 4, and that 3 times minus will come, so it is minus cos When you substitute instead of x, you will substitute 3, then it is cos 2n pi, which is 1. So I am just writing for now it is cos 2n pi upon 4n square pi square by 9. And I substitute 3 here, then it is also again sin 2n pi. Due to this will become 0. Then substitute 0 here in this place. So this is 0. So that's why this quantity will become 0. Here the quantity is left. Again there will be 3 minus is come because 1 minus here, another minus is there. So it is the 1 minus is with the, when I substitute the second limit, the another minus is there. So that's why 3 times minus will be there. It is 2 into cos 0, which is 1. Is 1 upon 4 n square pi square by 9. And when you substitute 0 here, the sin 0 will be equal to 0. So that will also become 0. So finally, you will have this quantity. So if you simplify this one, you take this 9 above. So and this cos 2n pi is 1. So that's why it is 2 times. So altogether it is 3 times. So 2 is already there upon 3 into 3 times 9 upon 4n square pi square. Here it will be 4 is there. So that's why it is, you will have 6. Here you will have 6. And this 6 will get cancelled out. 4 will get cancelled with this. So finally you will have 9 upon n square pi square. So finally your an is 9 upon n square into pi square. Next we need to calculate what is the bn. So bn is 2 by 3, 0 to 3 fx, which is 2x minus x square sine 2n pi x upon 3 dx. Again I am applying the generalized integration by parts with u, and this is I am to consider as b. So 2 by 3 is as it is. 2x minus x square is as it is. The integration of sine will be cos 2n pi x upon 3 upon 2n pi by 3. Then it is minus. So this is the first integration you will have. The derivative of this quantity will be 2 minus 2x. The integration of this quantity will be minus sine 2n pi x upon 3 upon 2n pi by 3 square. The next term will become plus, and that is the derivative of this one, which is minus 2. The integration of this term, which will become cos 2n pi x by 3 upon 2n pi by 3 whole cube. The next term which we have, the derivative of this quantity, the derivative of minus 2 will become 0. That's why next all the further terms will become 0, and the limit you have it is 0 to 3. And when you substitute 3 here, you will have some quantity, that is 2 into 3 is 6 minus 9, that will become minus 3. So you have minus 3 here, minus cos, when you substitute 3 here, it is 2n pi upon 2n pi by 3. That is the quantity left when I substitute 3 in the first one. When I substitute 3 here, this will become 0 because sine 2n pi is 0. Now this quantity is left. When I substitute 3 here, you will have, this will become minus, minus become plus 2 times cos 2n pi upon 2n pi by 3 whole cube. Then when you substitute 0 here, this quantity will become 0. Sine 0 is 0, so that's why this is also 0. and this quantity is left, and there will be a 3 times minus will come, so that's why it is minus. I substitute 0, cos 0 is there, and so the quantity left will be cos 0 upon 2n pi, and you just note that this two quantity will get cancelled out because cos 2n pi is 1 and cos 0 is also 1. So that's why, and this is of alternating sign, so that's why these two quantities are cancelled. Here this will become minus minus plus, and this 3 goes up, so it is 9. 1 3 is cancelled out, 2 is also cancelled out. So finally the quantity left in cos 2n pi is 1. So finally the quantity left is 3 by n pi. So that is your dn. And if you substitute now this value of a and dn in your function, then your function f of x, which is 2x minus x square in the interval 0 to 3 can be represented as a0 by 2, which is 0, summation n running from 1 to infinity an. The an you have, it is minus 9 upon n square pi square cos n pi x by l, which is 3 by 2. So it is 3 by 2 is there, so it is 2 by 3 plus summation n running from 1 to infinity dn. dn is 3 by n pi into sine 2n pi x by 3. The question was to calculate also the value of 1 upon 1 square, 1 upon 2 square plus 1 upon 3 square and so on. So you just saw that this is the n square terms coming here, which is here you will have n square term. So this quantity has to be 0. And if you want this has to be 0, your x should be 3. So if I substitute x is 3 here, this will become 0 because sine 2n pi you will have, and that quantity will become 0. So here, and the cos 2n pi will be plus 1, and you already have the minus is there. But in that case, you will not get the alternating sign if I substitute x is equal to 3. So if I want the alternating sign, I have to substitute x is equal to 3 by 2. So that's why this x is also cancelled out. So this 2 is also cancelled out. So it has to be cos n pi, and cos n pi we know it is minus 1 raised to n. So I am substituting x is equal to 3 by 2 in this expression. So this value we will have, it is 3 minus 9 by 4 equal to summation n running from 1 to infinity 9 by n square pi square into cos n pi, and cos n pi will be minus 1. So this is, this side you will have, it is 3 by 4, and this 9 goes into the denominator, this pi square goes into the numerator. You will left here, it is minus 1 raised to in minus 1 to infinity minus 1 raised to n upon n square, which is exactly this series. And to simplify this quantity, which will be pi square by 12. So that is the requirement to prove to the expression. So let us recall what we have discussed in this lecture. We have expressed the Fourier series in general any interval if it is given. You can able to find out the Fourier series of a function, and we have solved based on that 2 examples. That's it for this video. If you like this video, please press the like button. If you have any suggestion, comments or a question, please drop down in the comment box below. See you in next video. Till then, bye bye, sayonara.